This is 14.8, which deals with the concept of catalysis, and with this we will complete the chapter on chemical kinetics. So catalysis is a particular case, a particular factor that affects the speed of a reaction, and normally speaking, the catalyst will, or the effect of catalysis would be to speed up the reaction. But it's not the only use that you may have for a catalyst. You may also want to slow down a reaction, so that also qualifies as a catalyst. Okay, so anything that you add to the reaction that modify the speed of the reaction. So normally a catalyst, you would see that that's something that doesn't really is not involved in the reaction. But that still is a vague definition, because how can something possibly speed up the reaction if is not involved in the reaction? Well, let's rephrase that. A catalyst is something that you add to the reaction, but it will not show up in your overall reaction. So in this case, we have this. This is the reaction of interest right now. So it's the conversion of ozone to oxygen, and if we go a little more dramatic here, this is the destruction of ozone, the atmospheric ozone. Okay, something that you don't really want to happen, because if not, then we are not protected against UV rays from the sun. So normally this reaction would be very slow, but it just so happened that there are ways in which you can speed up this reaction. So for example, if you have this species here, this is atomic chlorine, and it doesn't have to do anything with radioactivity. It's just that it's not molecular chlorine, it's atomic, just the atom of chlorine. And here basically what is happening is that chlorine reacts very fast with ozone. So the atomic oxygen doesn't react as fast with ozone, but the atomic chlorine does react very fast with ozone. Okay, so and in this case, the one thing that I want you to notice is that this is a mechanism, and as such, if we were to add these two equations, then what it happens is we will get rid of chlorine, because here is as a reactant and here as a product. And this species here, ClO, a product there, a reactant here, you can cancel those two, and then you end up with your overall reaction. Okay, and because you are canceling those two species in the reactions, well, the first thing that might come to your mind is that, oh, they are reaction intermediates. But well, not so fast. Here, ClO is an intermediate. Okay, but the chlorine, the atomic chlorine, ClO, is a catalyst. Now, how do you notice, or how can you identify? Because you can look at a mechanism and you can identify out of that mechanism who is the product, who is the reactant, who is the intermediate, and who is the catalyst. Well, a catalyst is consumed early in a mechanism and then is regenerated later on the mechanism. So you are consuming here. So here is consumed and here is produced. And the intermediate is the opposite. The intermediate is produced early and then consumed later. Okay? Let me write that down. Let's use this. So here the intermediate is produced early and then consumed later. And let's complete this. Consumed early, produced later. So that's the main difference. They will not appear, both the intermediate and the catalyst will not appear on your overall reaction, but the behavior is different. Okay, once again, the intermediate is produced early and then consumed later. The catalyst is consumed early and then produced later. Okay, so that's the main way in which you can differentiate. If I give you a mechanism and I don't tell you anything about what each species is doing, just by looking at the mechanism and determining what your overall reaction, you can give me all the information that I need. Who is a product, who is a reactant, who is an intermediate, and who is a catalyst. Okay, so how do the catalyst affect the reaction? Well, usually what they do is provide a different pathway. Okay, remember, there is an energy of activation or activation energy that you have to surpass in order to produce the reaction. If you can lower it, then the reaction is going to go faster, and that's what you are looking for usually when you're using a catalyst. You want to speed up the reaction. Again, it depends on what reaction. If the reaction is too fast and you want to slow down, you can still use a catalyst. In that case, you call that a negative catalyst. But the ones that are used more frequently are the positive catalysts. Why? You want to speed up a reaction. Okay. So here, let's change. Here you have this would be the transition state, the normal transition state for the reaction without a catalyst. And then if you use a catalyst, then you are providing a different route for that reaction. Okay, so in this case, remember, you have a mechanism with 2 steps, so you have 2 bumps here because there's 2 steps. Okay, this is a 2-step mechanism, and that's why you see 2 bumps there. So each step will have a corresponding activation energy, and that's what you see in this graph. Okay, overall, the activation energy for any of those steps is smaller than the one from the uncatalyzed reaction, and that's why you have the reaction being sped up. Okay, so we are looking for substances that aim to lower the activation energy. Remember, there is a direct relationship between an inverse relationship between the activation energy and how fast the reaction is. The lower the activation energy, the faster the reaction is. Okay? Now, you can have those two, the catalyst, you can have it in 2 different modes, depending on what the availability or how you use those catalysts. So you can have a heterogeneous catalyst and a homogeneous catalyst. And the main difference is basically in what phase that catalyst is present during the reaction. And remember, you are conducting a reaction, right? And then you are adding something to speed up the reaction. But your product of interest is what's being produced on that reaction, right? So you don't want anything else that's going to be contaminating your final product. So you need a way to separate your product from anything else. So the heterogeneous catalysts are very popular because you don't need to separate anything. I mean, the separation is so easy that you don't even have to worry about. Okay, so an example of homogeneous catalyst is when the catalyst is in the same phase. The first reaction that we saw, the destruction of ozone in the atmosphere, that qualifies as homogeneous catalysis because the atomic chlorine, everything is in the gas phase. So there is no distinction of phases between the catalyst and your reactants or products. Therefore, that's a case of homogeneous catalysis. Now, heterogeneous catalysis, you have different phases. Usually, the catalyst would be in the solid state, and your reactants and your products could be either on the liquid state or gas phase. And a very common example here is the catalytic converter on your car that aims to reduce contaminants in your car's exhaust. And basically what you are converting is carbon monoxide to carbon dioxide. The VOCs to CO2 and water, and your NO2s or NOx, your nitrogen oxides, to molecular nitrogen. Okay, so these are better for the environment than the other ones. So that's why you have a catalytic converter on your car. Well, newer cars at least. So, but that's an example of heterogeneous catalysis, because you have a block of material there that when at high temperatures and when those gases go through the material, then they are converted to the other compounds. Okay. So if you have a picture view of what's going on, the yellow particles are your catalyst here and in here. The only difference is that that yellow particle is in the same phase here in the first case, same phase, and here is different phase. And remember, usually the catalyst would be in the solid state because it would be so much easier to remove it from your reaction mixture. Okay, so a classical example here, this is an industrial reaction, and basically you are just hydrogenating the ethylene to produce ethane. Okay, and that happens on the surface of a catalyst. Okay, everything happens in the gas phase, so you can have your solid catalyst supported in a container, and then you just flow the gases through the catalyst and the reaction will happen. There are some other requirements that you may need to consider, but if you want to explain this step by step, well, the first step is there needs to be an interaction between the catalyst and your reactants. So that's the first step. So those reactants have to adsorb to the surface, and then once absorbed to the surface, well, nothing is going to happen if the reactants will not be in contact with each other. Remember, one of the requirements for a reaction to happen is that they have to be in contact. They have to collide with each other. So in this case, they will do that at the surface. So they have to move around the surface until they find the other one. If they find the same particle, like in this case, if an atom of hydrogen finds another atom of hydrogen, nothing is going to happen. It has to be one molecule of ethylene with one atom of hydrogen, well, actually two atoms of hydrogen at the end, to produce the reaction. Then once they find each other, then of course they will react. The transfer of the hydrogen to the ethylene molecule will happen, and finally when you obtain your product, it will dissolve. Okay, will it stay absorbed to the surface? Well, up to a certain point it might. There might be some preference for the ethylene molecule to absorb to the catalyst, but eventually the product will leave the surface. The reactants eventually can also do that, but you are interested in the product. Now, one special case that we have with catalysis is the enzymes, because many of the biological processes that occur on our bodies happens because there are enzymes present to help the reaction, because normally those reactions would be rather slow. Now, Here, the enzymes act as a surface or an environment that will give the proper conditions for the reaction to happen. Again, what needs to happen? Molecules in contact, they have to have enough energy, and they have to be properly oriented. But when it comes to the orientation, that's where the enzymes do a superb job. Okay, the main reason why enzymes accelerate reactions is because that environment that they provide helps those molecules acquire the conformation, the correct position for the reaction to happen. Remember, we are talking about biological molecules, and biological molecules are rather large. Then you can imagine how difficult it would be for a large molecule to be in the correct position for a chemical reaction to happen. Well, enzymes take care of that, and they do that job very, very easily. Okay, as a super simplified view of what the enzyme does. Okay, so here is your enzyme, and this is the substrate, and the substrate, it's simply, let's call it the reactants. It could be one, it could be two, it could be three, it doesn't matter. It's just that symbolizes what the enzyme is going to take to produce the reaction. In this case, is assuming that you are breaking down this substrate, because here it's splitting in two, but it doesn't necessarily has to be the case. Well, it doesn't necessarily be the case. So here one particular example is the hydrolysis of sucrose to obtain glucose and fructose. And then basically what is happening is that water at some point has to get in there to break that bond. Okay? So it might be difficult because it's kind of a tight spot for water, and there are some other parts of the molecule that will kind of impede that the water gets so close to where it needs to for the reaction. But here the enzyme will do is hold, what it's going to do is to hold those molecules or that molecule in place, probably opening a gap for water to come in and facilitate the reaction. So that enzyme has evolved in such a way that has found the best way to orient that molecule so that water can enter and facilitate the breakdown of that bond. Okay, we are interested in that bond. That enzyme will make it a lot easier. Okay, so things to remember here. A catalyst does not appear in overall reaction. Excuse me. They are consumed early and produced later in the mechanism. And usually accelerate a reaction by lowering the activation energy or providing proper orientation. So that's how they usually act. Okay, so this video can be rather short for what you used to see, but that's basically what the catalyst does. Nothing to calculate, nothing to manipulate. The most that you may see is a mechanism, and you have to identify if there is any catalyst on that mechanism. Okay, other than that is knowing what a catalyst does, how they act, and of course could be homogeneous or heterogeneous, depending on how many phases you have when that reaction is happening. Okay, that means the catalyst usually for heterogeneous, the catalyst usually in a different phase. Okay, and that's it. That's all there is to know about catalyst.